So I'm going to talk about the data delusion. So the theme of my talk is really about, there's a lot of things you can do with deep learning, and that's great. But as you'll see, you know, we've sort of been here before, and I think it's worth, people talk about these hype cycles, and they talk about where machine learning or deep learning is on these hype cycles. Well, I think it's always worth bearing in mind that the underlying technology does not progress in line with the hype cycle. It progresses in some sort of constant rate moving forward, and we will hit challenges and problems with deep learning. There's things that it can't do. So my main talk will be about that and what I think is the real motivation behind the current advances in artificial intelligence, which I call the data delusion. Okay, so this is why I think we're advancing. So there's, do we have a pointer actually as well? Nikita, pointer? Sorry, I should have checked before. So this plot here is from a science paper from 2006. You can tell it's 2006 because there's quaint things on the right-hand side like mini disks, and various other digital types of storage. What it's trying to show is an estimate of the information storage capacity in the world. I took it from the Wikipedia page on big data, so you can find it there. It's a recolored version of that. And what it shows is that sort of going back to sort of 1986, most of the world's information was stored in analog form. So VHS video, or for those of you who remember, Betamax, and these type of things. And that continued to be the case until, thank you, until about 1993, when you start to see a significant amount of digital storage. So they're listed on the right-hand side here, the type of digital storage that's there. So you've got CDs, mini disks. I mean, CDs, I suppose, would be the big thing that really starts taking up. But before that, you've got analog LPs, tape cassettes, all in analog form. In the end here, on the right, what you'll see is it's sort of trying to assess how much information is in the world in 2007 and how much of it is stored digitally. So 2007 is before like the big era of mobile phones. So just imagine how much this has increased since then. So 2000 is this is a misrepresentation on the plot. 2002 is what they define as the beginning of the digital era. So the time at which the amount of analog stored information was outweighed by the amount of information we stored digitally. Now, it's not all about storage, of course. It's about interconnection. But once you've got information stored digitally, it's easier to interconnect. So how does that relate to deep learning? Well, convolutional neural networks were developed back in the 1990s. Also, recurrent neural networks, the sort of techniques people are applying now. They were developed in the 1990s. I know because I entered machine learning when it was the field of neural networks because I was interested in neural networks. I saw Jan LeCun speak in 1997 talking about digit recognition with convolutional neural networks. But by sort of 2002, by this era here, a technique known as the support vector machine was dominating NIPS, which is probably the main conference on machine learning. And the reason primarily is because we did not have the level of data at that time to make those models work. And I'm going to try and give you a sense of why that is in this talk and why I think that that will become a problem once again. So, you know, broadly speaking, I read actually the last one of these meetings, Deep Learning Summit, I was sort of invoking the 1990s. When you hear people talk very often today, you hear them saying the same things people said in the 1990s. Genuinely, you do. They say them at a different scale. And the sort of challenges we're solving today are much greater. But people made the same kind of promises 20, 25 years ago. I'm going to keep doing that. So what I want to do is introduce a little analogy for you. So who here has heard of Thomas Newcomen? 1, 2, 3, 4. It's terrible, terrible. Okay, who invented the steam engine? Thomas Newcomen wasn't the first, actually, but he's the first one to make a practical model of the steam engine. And this is his engine. So his engine actually heated coal. Heated coal. It burnt coal to heat a cylinder. And the way it worked is it sort of squirted water into the cylinder, and it boiled the cylinder, pushing the piston up. it's not so much the pushing, it's the pull stroke. And it squirts water in to condense, which pulls this chain down. And he invented it. He was, I think, 1712. He was a Cornishman, and he was inventing it to pump out tin mines in Cornwall. So the engine worked by basically having a load of coal in here that heats a cylinder that's filled with cold water, causes steam to arise, and then squirts cold water back into the cylinder again. So sucks the cylinder down, pulling a chain down. Now, the interesting thing about his engine is that the coal, so I'm at the University of Sheffield, which is about here, right in the middle of this big coal field, South Wales, up around Newcastle, the Scottish coalfields. That's where the coal is. So Thomas Newcomen was down here in Cornwall and was inventing this engine to pump out tin mines. But it was so inefficient that his engine never really found application in the tin mines he was interested in. It found application in coal mines because they could mine the coal and they could shove the coal inside the engine. So the tin is down there. Now, compare that to the modern era and data. So the equivalent situation is that we're building inference engines that can work on data, and companies the size of Google, Facebook, and Amazon have enormous amounts of data. They're like the coal mines. But startups or many application areas, like the tin mines, they don't have the data that they need to power the intelligence being equivalent to pumping out the coal. And I think that this is very much the situation we're in today. The companies that can make the most out of machine learning technologies are the large sort of internet companies. Microsoft, I could add there as well. But this is a problem. So this is an image to represent an application area that's very, very close to my heart, which is health, personalized health. Working out how to make people better. And data is key. So understanding people's health, you can do it through data. But what's going on at large internet companies is they're doing an enormous amount of labeling of data in order to get hand labeling, creation of data, acquisition of data on the internet in order to get data sets large enough to do these deep learning models. Now, it's generally considered unethical to force people to become sick to acquire data. That's not going to happen. And there are rare diseases, such as genetic diseases, that are rare variants, where you're only going to get a very little data in. So you're never going to be in the situation we're in. If you look at all the application domains where deep learning is successful, you'll see they're domains where we can acquire a lot of data. They tend to be things like where we're mimicking humans, what humans can do. The first deep learning success in vision was based on very, very large labeled data sets. The way that we do large-scale speech recognition systems is people transcribing enormous amounts of speech, labeling it all. And all these systems use way more data than any human uses to achieve the same task, like orders of magnitude more data. So if we want to get into these sort of domains, we kind of need to deal with that. Now, this engine is not quite invented, but it illustrates the sort of thing that I want to point out. So what was James Watt famous for? Everyone thinks James Watt invented the steam engine. James Watt didn't invent the steam engine. He was about 70 years after Newcomen, and he worked on a Newcomen engine, and he realized it was a waste of energy to heat and cool this cylinder all the time, and he invented the separate condenser represented there. Actually, he did a hell of a lot more than that. This is a Watt engine. He invented gears for turning it into rotary motion. He developed a governor to control speed. He developed all sorts of linkages, and down here is his separate condenser. That made the steam engine much more efficient, and that's what triggered the Industrial Revolution. So that's why, 1784, I think, his first engines formed. And of course, the 19th century is dominated by steam power. Whereas 70 years before, Newcomen's engine was developed, and of course, it had less of an effect. So machine learning needs its separate condenser moment. We need practical methods that are data efficient, yet have the representational power of deep learning models. Okay, so this is an image of a deep network that I've taken from the Deep Face paper from Facebook. I like to think of it as a Callista Flockhart detector, although it's actually a face detector. It's actually for face recognition. So the idea is you present two faces to this model and you ask, is this the same thing? Now, the interesting thing about these models is that they have a lot of parameters. So this is the form, this is the pictorial form. So we've got an image coming in, and then it's represented in its channels. So actually they take Callista's face or whoever's face they find, and they try and map it back to a sort of 2D. They project that around, I think, using geometric techniques. I think if you're in the US, I'm not 100% sure about this, your face is being processed by this thing on Facebook. Here, I think in the UK or Europe, it's not because of privacy laws. So you're turned into red, green, blue channels, and then you're mapped with nonlinear functions into different things. And the output of these functions is being represented. So you're being turned into a higher dimensional space. Each of these things is showing, taking the image and mapping it in a different way. And then it's going through each of the models. Here you can sort of see it looks a bit like the face, but eventually it gets transformed into something that doesn't look much like the face. And in the end, it gets transformed into a label yes or no. Is this the face or not? So mathematically, this is actually quite a simple object conceptually. It's what's called a composition of functions. So we're taking a face as an input x, and we've got a very complex high-dimensional mapping at each stage, composed functions to get an output, which is yes or no. Is this the face of Callista or not? Now, what's complex about it is the nature of those functions. But I think one way of thinking about it is, you know, a lot of people seem to like to say, oh, deep learning is so complex, you just can't understand deep learning. Well, maybe we can't understand everything about it at a level, but you can get an intuition for what's going on. And the intuition I like to have is coming from this old-style pinball machine, or a pachinko machine, I guess we'd call them today. But this is a French one, I think, from the 18th century, similar to the Watt engine, where you've got a ball coming in the top and it hits these layers of pins and it gets bounced around until it comes out the bottom. And typically in these machines, at the bottom you might have a score. You might have 100 points on the left and minus 100 points on the right. So your objective is to fire the ball in such a way that it comes out and you get good points. Of course, modern pinball machines have a lot more sophistication, but the old ones have just this very simple setup. Now what I want you to think of is I want you to think of each of these rows of pins as being like those functions. So the output of one function going into another. So the x, the input, is the location of the ball along this side here, and as it goes through the machine, it gets transformed from left to right as it's going through the machine. So each layer is equivalent to one function. Of course, the whole thing represents a function, but it's a composition of these different functions, and that's where you get the complexity. Now, the interesting aspect of these functions is that they're parameterized in manners like this. So I think of them as basis function models, but they contain all these weights, all these parameters. Now, analogistically, I want you to think of those weights as the location of the pins. So the model we're showing, if we think of this little representation of these functions here, so at each stage, we've got this sort of function mapping, which I've now turned the f into this phi of w to represent the weights. The location of the pins represents the parameters of the model. Now, in this system, we have a one-dimensional input, so the ball can enter anywhere across the top here, and then it goes down, and then we've got a yes, is it Callista, or no, it's not. So this would be equivalent to representing Callista with 1 pixel. So we've only got 1 pixel of Callista. In reality, what's going on is this pinball machine's happening in hyperspace, very, very high dimensional. So these pins are really, they're like planes, they're slopes, it's crazy. You can't even imagine it. So just think of the pinball machine. So what you get is you might initialize your model, and then you've got a point that is Callista, a data point represented by this ball, and then you throw it through the machine, and the machine gets the answer wrong. You try another ball, it goes through the machine, and it gets the answer right, so you're happy. So that was Callista, and the machine said yes. Here's a ball that wasn't Callista, but the machine says yes. So the training stage of machine learning, the thing that takes all the time and all the compute, is sorting this out. Moving the pins around such that the yes one now goes into yes, the no one now goes into no, the yes goes into yes. This is the difficult bit. Now you've got the conception right about what's going on, why this is so challenging, because you can see the balls don't go all the way every path through the machine, and the machine itself is very, very high dimensional, right? So the machine itself has many, many more pins in many, many different configurations. So one of the challenges is that there can be parts of the machine that you've never sent the balls through before. Now, we've got people from DeepMind here, but I think it's the case, and they can correct me later if I'm wrong, that when AlphaGo lost a game, it lost a game because Lee Sedol pushed the machine into an area where it had never seen before. He pushed the ball, he managed to find a place where the ball was going into the neural network, and it hadn't seen that sort of area before. I don't know that's correct, but I think that's correct. I heard that was indirectly that was correct. But I can be corrected if that's wrong. And that's often when things go wrong with these deep learning models. So another thing you'll find is there's work on sort of making slight changes to the inputs of the neural network to fool the machine to say it's something else. So you can sort of have a picture of an ostrich. You can make slight changes to the image that have no effect on a human. Did I say an ostrich? And you can have it detected as a car. And the reason is because you're changing the input just slightly so that this ball goes down the wrong path through some bizarre route of the machine you've never seen before. And that's a serious problem, because the way around that is to pile buckets of data in. Buckets and buckets of data to try and explore as much of the machine as possible. So that's the challenge. That's the problem with deep learning at the moment. And the solution is this, that instead of looking at single paths for these balls to go through the machine, you look at multiple paths. So what you do is, instead of looking at the machine and saying, one ball can only go one route through, you look at the ball and you say, what happens if I perturb this slightly and push it through? What happens if I move all those pins around and see what the path is through? And you make sure it's robust to that sort of thing. Unfortunately, this is a lot more computationally intensive. So what it actually involves is integrations. That's why it's a problem. So the reason deep learning works and everyone can do it and run these things is because you can compute gradients of this model. So you move those pins around by computing the gradient of the objective function with respect to those location of the pins, which tells you how to move the pins. But if you want to do what I just proposed, you have to integrate over all the possible paths that you can get through the machine. And for those of you who did calculus at high school or university, you should know integration is a lot harder than differentiation, and often impossible. And it's impossible for these models generally. But there is a class of models known as Gaussian processes where integration is possible. And with this class of models, what you do is you propose a set of functions. So this is just one set of functions now. You look at your data, and then you reject functions that don't conform to your data. So you sustain a belief in these multiple paths. So this is the sort of area that's been interesting me, but I'm also very interested in these hierarchical representations. They're very, very powerful. I was very persuaded a long time ago. Jeff Hinton was pushing these models, I think even 2001. I was a postdoc at Microsoft Research in Cambridge, and Jeff was talking about these models. I think that they're very important for other reasons, but they make this process, which is great for Gaussian processes, quite difficult. So what we've been trying to do in Sheffield, and I'd say everything I've talked about is obviously, because I've only been at Amazon for 3 weeks, is all work I did at Sheffield over the last 10 years or so. What we've been trying to do, and see with some of the people involved, Niccolo Fusi, who's now at Microsoft Research in Boston, Max Wiesler, who's still a PhD student, Alan, who's a PhD student, Shen Wen, who's moved to Amazon with me, and Fariba, who's a PhD student. Build these models in such a way that we can represent things like clinical tests, treatments, survival analysis is very important in clinical data, biopsies, X-rays, as a function of genotype, environment, and epigenotype. We cannot do this. I keep giving this talk, and then people afterwards say, that's an amazing model, and we can't do it. This is my conception of what we're going to do. What we can do is segments of it, and there's papers, we've got papers in Nature Methods, PLOS Bio, etc., that take parts of this model. They take your genotype and your environment, and they try and predict your gene expression. Those models all work really well, but we're seeing it as a jigsaw so that we can piece these things together. And we do it with Gaussian processes. So instead of just a simple function, we use probability distributions over functions. How am I doing for time? I've got 43 seconds. So I had a couple of more comments. So the reason we want to do that is because I think one of the most powerful ideas of these models is that you've got the ability to go from things like your state of health, which is a very abstract notion, isn't it? I mean, your state of health is like how your doctor assesses you, how your partner thinks you're feeling, how you're feeling when you get up in the morning. Like yesterday I had a headache, today I didn't. But actually that's related to your organ states and your cell states. So at the fine level, you are not a sort of coarse abstract thing. You're an enormous number of cells with a load of biochemical reactions going on. Now, deep learning really does offer the promise. This is, for me, one of the most interesting things about it, to have models that have that level of abstraction in them. So the cell states go out to biopsies and X-rays directly, but that doesn't actually, that's a very complex process to understand something about what your clinical tests would be or your state of health. And that's where I think deep learning is, for me, offers so much promise. But when you do it probabilistically in particular. So I had some other comments, but I'm going to skip those. They're different analogies. And just say thank you. So you can sort of see more. I've got blog posts about this type of idea, this concept. You can see talks from me online from my website, or you can follow me on Twitter or whatever else. And